the C standard library file, header file that has some functions that operate on strings. So we looked at a few functions last class. Today we'll look at a few more. And then I think I'm going to stop midway through the next deck of slides and I'm going to jump to a different deck. So I'll explain when I get there. All right, so strings are just arrays in C, right? And so if you want to test if two strings are the same, you can't just compare if their arrays are equal or if the pointers to the two strings are equal. That doesn't work, right? So remember, if you have two pointers, so a string S and T, where S and T are pointers to car, or arrays, it doesn't matter, right? If you write S equals T, two pointers are equal if they point at the same memory address, right? But that doesn't mean the strings are equal. You can have two strings or in two separate arrays. Therefore, they have two different memory addresses, but they're still equal, right? They contain the same sequence of characters. So equals equals and not equals doesn't work for comparing strings, right? So it doesn't do what you want it to do, right? You can, in fact, compare two pointers for equality, but that's not the same thing as comparing two strings for equality. So you should use string CMP to compare two strings for equality. String CMP works the same way as compare does, or compare2, sorry, for Java strings. And it would work the same as less than, greater than, or equal to in Python. So if it returns 0, then that means the two strings have the same sequence of characters, right? They have the same length, same sequence of characters. If it's not 0, then they're not equal, right? So either their lengths are different or their sequences of characters are different. But it returns extra information as well. Right? It actually compares the two strings lexicographically or in dictionary order. Right? So if the left-hand side comes before the right-hand side in the dictionary, then you get back a negative value. If the left-hand side comes after the right-hand side string in the dictionary, then you get back a positive integer value. The integer value does give you some information. It's not always used. Right? It tells you the difference between the two characters where they first differ in the strings. Right? Of course, these are C-style strings, so again, they have to be null terminated. If they're not, anything could happen. Right? The dreaded undefined behavior. So there's a little program that you can run here. You can type it in and run. It just tests if your two strings on the command line are equal. I guess we haven't done this yet. So we haven't looked at command line arguments. Oh, no, we have done it. We have looked at command line arguments in C. You did it on your first assignment. That main method here is a main method that accepts command line arguments. Right? Arg count is the number of command line arguments minus 1.
No, plus 1.
Sorry?
Plus 1.
Arg count. Sorry, plus 1, thank you. It's plus 1 because it includes argv0 is the name of the program. So argv is an array of strings, right? And thus its funny-looking declaration, right? So notice that argv is an array, so argv square bracket, so it's an array, right? The element type is whatever's in front of it, so that's car star, right? So argv is an array of pointers to car, or in other words, it's an array of strings, probably an array of strings. Right? So if you want to compare the first two strings on the command line arguments, they're arguments 1 and 2, not 0 and 1. Right? 0 is the name of the program. So argv1 and 2, those are the first two. Those are the two strings that were passed in as command line arguments. Right? If you compare the two, if you get back 0, they're equal. If you get back a negative value, then the first string comes before the second string. And if you get back a positive value, the first string comes after the second string. So if you want to, you can type that in and run it, and it will run. Oh, okay. So there's a strings part 2 deck of slides called right here. All right, so if you want to search this string for a character, then you can use strchr. Right? And so that finds the first occurrence of the character ch in the string str. Right? So it returns a pointer to that character, or a null pointer if it doesn't find the character. Right? So this is sort of like index of in Java, except instead of returning an index, it returns a pointer. If you want the index, it's easy to get the pointer. Right? So if you want to get the index from So if you have, so if you get char star P equals str chr, something, whatever, right? And my string is S, right? And then you can get the index as, it's just P minus S. That's not an int, sorry. That's, I guess strictly speaking, that's pointer difference type. Right, so ptr diff underscore t, that's the type in C that can store the difference between two pointers. I think on most systems it's unsigned long int, right? It's just an unsigned value. Sorry, it's long int. It's not unsigned. It can be negative. So it's long int. Assuming p is not null, that will give you the index of the character, of the first character of the string that you're looking for. ch is not a char. It's an int. And that's for historical reasons. So this is one of the first functions in the C that was created for the C language. So long time ago in the 70s, characters were just ints. And so that's why it's an int there. But it's actually expecting a character. Extra examples, if you want, you can click on that link, and it'll take you to a little main method where there's a bunch of examples using this function. Right? But it just looks for the location of a character in a string. If you want the last location, not surprisingly, there's another function. This time it's got a little r in it. This is one of the things you have to get used to in working with the C library. The difference between two functions is often just in a single character in the name of the function. So you have to be very careful when you're typing in C function names, because it's easy to make a typo and you end up with the wrong function. So this one finds the last character. Whoops, sorry. Last occurrence of ch in a string, or null if it doesn't exist in the string. Oh, here's how to get the index. So what am I doing here? So the program is the index of that character in that string, right? So you pass in a string and you pass in a character. Notice to get the character, it's a little bit odd in this program. So your command line arguments are strings, right? So your character is in the second string, right? Is the first character of the second string. So your second string is argv2, right? The first character of that second string is the character at index 0, right? So notice the double square bracket indexing, right? This also suggests that argv, you can treat it like a two-dimensional array, which you sort of can, right? So argv2, second character in that, second string in that array, right? Square bracket 0, first character of that string. And then I'm just using pointer subtraction here to get the index of the characters. Right? If you want to search for a string in a string, then that's string. Right? So string will search that string for that substring, right? And returns a pointer to the first occurrence of that substring. Right? So similar to the other two functions, it's just looking for a string now. And this one's a weird one. So this is a very odd function in C. So the function is strtok. And so what this thing is, it's the function that tries to tokenize a C-style string. And so the idea here is that you have a string, and that string is made up of a bunch of different fields. Each field is separated by a specific character, right, called dlim, right? A character or characters. Any character in that string dlim can serve as a separator character, right? And so what this function will try to do is it's going to try to break up str into the separate fields. But the user has to call the function over and over and over again to get the separate fields. So it's a bit odd the way you use this thing. All right, so let's go through this slowly. So when you call this function, it returns a pointer to the next token or field, right? So it returns it returns a pointer to the next field in the string, right? If it can't find the next token or field, then it returns a null pointer, right? So if this thing returns null, you know that you're done splitting the string into its individual pieces. Okay, if the string is not null, right, then the function assumes that this is the first time you're going to call the function to split this string. Right? So one more time. If that thing is not null, then the function, oh, sorry, I know there's a bunch of spelling mistakes. I accidentally inserted a K everywhere. And it probably it happens a lot, sorry. Let me see if I can go back. So once I did it once and copied it, it just shows up everywhere now. Okay. Okay, so if that thing's not null, it assumes it's the first time you're trying to split that string. If it is null, then it assumes you've already split this, you've already gotten one or more tokens out of the string, and you want to get the next token. Right? So the way this thing works is you keep on calling it until you run out of fields or tokens in the string. Right? Each time you call it after the first time, you pass in null as the string. As soon as you pass in a non-null string, it thinks you're trying to split a new string. Right? And so it's a function that has memory in it. Right? So in other words, it remembers that it's splitting some string, and it remembers that it's splitting which string it's trying to split. All right, so if it's not null, then the thing assumes that you're trying to split the string for the first time. So the way it works is it searches for the first character that's not one of your delimiter characters, right? So not one of your separator characters here. Right? So it searches the string, it's looking for the start of the first field. Right? So if it finds one, then it searches for the first occurrence of the character that is a delimiter character. Right? So now it keeps on going. When it finds one of your splitting characters, it stops. And it replaces the splitting character with the value null, right? 0, the numeric value 0. Right? So it actually inserts a null terminator into the middle of your string, right? At the end of the first field. Right? It then returns a pointer to the first character that was not a delimiter. Right? And so when you try to print that string, or when you try to print the string that's returned as that pointer, right, it prints the first field because the function has inserted the null terminator into your string to indicate the end of the first field. Right? So this function actually destroys your string. Right? It inserts one or more null terminators to mark the end of each field. Right? Each time it processes a field, the pointer that it returns is the pointer after the null terminator that it inserted. Okay, so if the thing is null, right, then the function assumes you're trying to get the next field from the string. Right? So it continues from where it left off at the previous call. Right? So it's starting at the character after the first delimiter. Right? It's now going to search for a character that's not, it's going to search for a character that's not a delimiter. Right? When it finds one, that's the start of the second field. Right? Now it's going to search for the next delimiter, right? And that'll be the end of the second field. And then again, it inserts a null terminator. It replaces the delimiter character with a null terminator character. Right? So the function is destructive. It writes a bunch of null terminators into your string, right? So it marks the end of each field with a null terminator. So if you're going to destroy the string that's passed in, right? So if you're going to affect that string that's right there, right, then that string here cannot be a const string. Right? And so what that means in C is that, so one, it can't be const string, but it also can't be a string literal. Right? So you can, where'd it go? So you can't call the function passing in something in double quotes, right? Because a double quoted string in C is read-only, right? You can't write into it. All right, so here's a little function that uses strtok. So I have my string. It can hold up to 80 characters. Right? I'm going to use the colon as the character to separate fields. Right? One or more repeated colons are merged together. Right? So if you have multiple delimiters side by side, they all get merged into a single, or they're all treated as though they were a single delimiter. Right? And so what that means is you can't have empty fields, or this function cannot parse empty fields. Right? So here I've got colon, 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 and then field 1. right? Colon, colon, field 2, colon, field 3, and then 3 colons, field 4. Right? So there's 4 tokens in this string, field 1, field 2, field 3, and field 4. Right? So I'm going to call strtok, passing in that string and saying that my delimiter character is the colon. Right? So the first time you call this, right, it starts at the beginning of the string. Right? It looks for the first character that's not a delimiter. So colon, 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 F. Right? So it knows that the F is the start of the first field. It remembers or stores a pointer to that F. Okay? It then keeps on going. So IELD1 colon. So now it finds the first colon after the start of the first field. So it writes a null terminator over that colon. Right? So inserts \0 into your string. Then it returns the pointer to the F. Right? So when you get the pointer to the F, that's the null terminated string FIELD1, right? Because it inserts the null terminator here. Okay. So if it returns non-null value, that means it's found a token. So I can now process the rest of the tokens. Right? So I'm going to print the first token, and then I'm just going to call strtok again to process the remaining tokens. Right? You pass in null to indicate that you want to process the string strtok was last processing. Right? So remember, it's got a pointer to the F. Right? It's written a null terminator right there. Right? So when you call this the second time, it's going to start at that null terminator, and it's going to look for the first character that's not a delimiter. So it finds a colon, that's a delimiter, so it keeps on going. So now it finds an F, stores a pointer to that F. Now it looks for a delimiter, IELD2 colon. So it replaces that colon with a null terminator and returns a pointer to that F. Right? And so you end up getting the string field 2. Right? One more time. Right? So it remembers you left off at the colon. So it looks for the first character that's not a colon, finds the F. Right? Keeps on going until it finds a colon. So here, replaces that with a null terminator and returns a pointer to the F from field 3. Right? When it finishes processing field 4, it knows that it's hit the end of the string because there's a null terminator sitting right there. Right? So if you try to call it again, it'll return null, right? Indicating that there are no more tokens left to process. I guess the question I have for you is, how does strtok remember where it was in the last call? So how do you write a function in C that has memory? It's yeah, but what type of object would you need inside the function? So it has to be inside the function, right? So strtok must have something inside of it that remembers where the last character was, right? So it's going to have a pointer of some kind, but what does that pointer have to be? It has to be marked as being, it's static, right? It's static because static variables, they're remembered by the function between calls to the function. So the way this thing works is that there's a static pointer to a character in there, and it just remembers where it was in the last time you called the function. So there is an example of when you might use a function, a static variable in a function. It's very unusual. So this is one of the few functions in the standard library that does this sort of thing. Right? So if you actually print out what it did to the string, you can actually see how it works. Right? And so what is this program called? Tokenize. Okay, so what did it do to the string? So remember our string was colon, 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 field 1, and then there was a colon. So you can see there, it replaced that colon with the null terminator. Right? Then there was a colon, and then field 2, right? And then it replaced that colon with a null terminator. Right? Then there's field 3 and a colon, so it replaces the first colon with a null terminator. Right? Colon, colon, field 4, and then it's done. Right? The way I print out the string is I have to manually look for. I just loop over the characters of the string. Right? I know what the original length of the string was. Right? That's why I took the string length back here. So I know how long the original string was. Right? So I can loop over the original, the length of the original string. right? And I can just access each character of the string, right? If that character is not 0, right? So if C, right? I'm going to print out the character. Otherwise, I print out null, right? So you can see where all the null characters are in that string. I guess these are null terminators. The language is odd in the use of the word null, right? Okay, so it turns out that many common tasks that involve reading data from a file, often when you're reading data from that file, that data is separated with some kind of delimiter, right? So it's really, really common. Most spreadsheet programs will output or read something called comma-separated value files, right? So in other words, you have a spreadsheet, it's got a bunch of columns. It will output each row, where the data in each row is separated with a comma. So it typically quotes the value in each cell. Then there's a comma, and then the next quoted value, and so on and so on and so forth. Right? So comma-separated values are very common. That's how I have to give OnQ your grades for a quiz or an exam or something like that that's not marked on OnQ. Right? So if somebody if somebody gives me a spreadsheet with your grades, the way I give it back to OnQ is with a comma-separated value file. Tab-separated value files are super common, especially when you work with databases. So a lot of databases will output or import data from a tab-separated file. So in other words, the fields are just strings, and then they're separated with a single tab. Right? So you would use, if you were trying to parse that thing, you would look for the tabs inside the file. Okay, so I want to stop there for right now, because the next part in this deck of slides is trying to read stuff from a file. I actually want to go back a little bit and use some structures to implement a data structure. So I want to go back and look at how to implement a list in C. Array-based list. Okay, so for some of you, you're in there are some students in the course who are in 124. We haven't actually implemented an array-based list yet. So you're actually going to do that first in this course as opposed to in 124. So I have to talk a little bit about how lists work. So for many of you, especially those of you in second or third year or fourth year, this is going to be a review. The source code is on OnQ. So if you just look on the lectures page, you'll see a little zip file called list.zip. And you can get the source code for this. We're going to use some new functions here. So we're going to use memcopy and memmove. So those are the two functions that that copy blocks of memory or move blocks of memory. And then I may skip over this, look at this function called sprintf. Okay, so a list is just a sequence of elements of some single type, right? So you can have the elements in the sequence, they're indexed using an integer value, right? So 0, 1, 2, and so on and so on. Right? C is not Python, so you don't have negative indexes. So you only have non-negative indexes in C. Right? The size of the list is the number of elements in the list. Right? So the empty list has 0 elements, or a size of 0. If you have an array-based list, then you have to worry about the capacity of the list. Right? So how many elements can the list hold? Right? And so that's called its capacity. Right? The capacity is different from the size. Right? Size is the number of elements in the list. Capacity is maximum number of elements you can put in the list. So when you add to the end, so adding an element to a list, it depends on how your list data structure is defined. In some cases, adding to a list adds at the end of the list. Right? So if you have one element in the list, then it adds the element after the first element. Right? Then it adds the element after the second element, and so on and so forth. Strictly speaking, you can implement a list where you insert at the front of the list. Right? So when you add an element to the list, it adds to the front. We're going to add to the back. Right? Of course, when you add an element, that increases the size of the list by 1. And finally, you can have a fixed size list, so a list whose capacity never changes. But it's often convenient that you want a list whose capacity can change as needed. Right? So if you start out with a capacity of 8, and you want to add 20 elements to it, the list just increases its capacity somehow, right? So that it can hold the extra elements. So it's nice if you can automatically increase the capacity of the list. Right? So there's a picture of an empty list using an array. Right? So I have an array of size 8. There are some values in the array because it's an array of something, so there are values in the array, right? But the size of the array is 0. So as far as we're concerned, there are no elements, or there's no valid list elements in this array, right? And what that means is that there's no valid index that I can use on this array, right? So if I try to get or set element 0, that doesn't work, right? Because the list is empty. Okay, so if I add an element to the list, right, then that element gets inserted at index 0, right? So my size is now 1. The capacity doesn't change, of course, right? But now I have a valid index, right? So I can use index 0 for stuff. I can get or set the element at index 0. I can remove the element at index 0, right? Add another element, and now you have 2 valid indexes, 0 and 1, right? And so on, and so on, right? So notice that the valid indexes are always between 0 and the size of the list minus 1. Right? So to get or set an element, you're just going to use the index, right? So if I want to get the yellow element, right, I would just ask the list for the element at index 3. If I wanted to change that element to something else, I would ask the list to set the element at index 3 to some value. Right? Typically, you're not allowed to set or get an element at an invalid index. Right? So for this list whose size is 2, I can't ask for or set the element at index 3, unless this is a bash array, in which case you can. Right? But this isn't bash, so we're not doing it that way. All right, so in a resizable list, if you have a full list, you have to increase the capacity of the underlying array. Right, so here I've got a full list. If I want to add another element to this list, right, I don't have room, so I need to make room for that new element. Right? And so the way you do it is you expand, or you make a new array that's bigger than the existing array, copy all the elements from the old array into the new array, and then add the new element. Right? So that requires making a new array and copying elements from the old array. Right? So let's back up a few slides. Right? So notice that to add to a non-full list, right, all you're doing is just setting an element of the array. Right? So that's always in O1, because setting an element in an array can be done in constant time. As soon as you try to add to a full list, or to a list whose size is equal to its capacity, right? Oops, you have to make and copy all of the existing, make a new array and copy all the existing elements. So adding to a full array has complexity big O of n, right? Where n is the current capacity of the list. Okay, if you want to insert an element into a list, into an array-based list, right? So I'd like to add an element at index 4, right? And so what you have to do is you have to move a bunch of elements over to the right so that I can make room for that new element, right? So all those elements that are in red, I have to shift those one position to the right, right? And then I have space for the new element, which I can insert, right? And so adding into the middle of the list involves moving a block of elements, right? So that's what I'm going to use mem_move for. Sorry, mem_move or mem_copy. I'm going to use mem_move for that, right? So there's a function in C that lets you move a contiguous portion of memory, right? So in other words, you don't have to write a loop to move the elements yourself, right? You can ask a standard library function to move a chunk of elements for you. Inserting at the end of a list is, oh yes, this is just inserting. So this is the insert function. So when you insert into a list, you're supposed to give it a valid index, right? So 4 is a valid index for this list. 10 is not a valid index for this list. Most implementations of insert will let you insert to the end, though. So in other words, if you try to insert at index 10, this should work. So it should just add the element at the end of the list, right? So it's slightly unusual because the index is not technically valid, but it should work anyway. And it's easy to implement. You just call add, right? Because that's what add does anyway. All right, so if I want to remove an element at a specified index, right, I'd like to move the element at index 4, right? I can't leave a hole in the list, right? So what I have to do is I have to take all of the elements after the one to remove, and I have to shift them one position to the left, right? So all the elements in red, I have to move one position to the left, right? And again, I'm just going to use mem_move to do that rather than writing a loop. Right? The loop is actually the loop to write to implement these to shift a bunch of elements around. You have to be a little bit careful when you implement them. One has to work in reverse order, the other one has to work in forwards order, right? Otherwise, you end up overwriting elements of your list. Right. Okay. So that's how we're going to do it. Okay. Now, because you can't, when you're using a list, many of the functions that operate on a list are based on an index, right? Now, in C, you could say that the user is responsible for providing a valid index. If they don't, it's their problem, right? But that's not normally a nice way to implement a data structure, right? Normally, you want to do some error checking for the user, right? Like Python and Java do. So we're going to do the same thing. Now, the problem in C is that there's no standard way of doing error checking. So there's no exceptions. And there's really no standard way to indicate that an error has occurred. So the way we're going to do it is we're going to use this thing called assert. Right? So assert looks like a function. It's actually something called a macro, but whatever. It's for us, it looks like a function. Right? You can assert a condition. Right? So if the condition is true, assert does nothing. Right? If the condition is false, assert will stop your program. Right? So that causes a running program to terminate if the condition is false, right? So it's sort of like a Java exception, not really, but sort of, right? It does kill your program, right? The nice thing about assertions is you can use them while you are debugging and developing, and then you can turn them off when you're done, right? When you're sure your program's correct. So you can disable them via a command line option. All right, so let's look at the source code, because this is a bit of a beast. Okay, so like any, so this is going to be, we're going to provide a data structure for the user. And so the correct way to do this is to split our list implementation into two files, right? So one is going to be the header file. Anybody that needs to use our list, they're just going to include our header file into their code, right? And now they have access to all of our list functions. But the actual implementation of the list we're going to hide inside of a separate file. So here's my header file, and here's my source code file. Right, so I've got a list.h and a list.c. Right, notice that list.c includes its header file. Right? Okay, so here's list.h. There's my include yard. Right? I'm going to use a standard bool, so I can write bool everywhere instead of using an int. Now, the first thing people are going to need is they're going to need our data structure. So I'm going to declare a type def called list as our list data type, right? So if anybody who wants to use our list, anybody who wants to use our list can just use the name list, right? But the actual type of the list is a structure, right? So there's actually some structure called list that represents the actual data type, right? The structure isn't in the header file, right? And you might think that's weird, right? The structure is not actually defined here. Right? And in C, that's okay. You don't have to define anything before you can use it. Right? All you need is the declaration. Right? So as soon as I've declared that this thing called list exists, I can use the name list throughout this header file without any issues. The definition of the structure is inside the source code file. So there's my list structure right there. Right? So our list structure consists of, well, it's going to be an array-based list, so I need an array to hold the elements. So there is my pointer to an array. Right. So I have an int. So this is going to be a whole. This is for a list of ints. So I have an array of int. Right. I have the capacity of the array, right? Because remember, you don't know. C has no way to remember how big a dynamically allocated array is. Right. So I have to remember that. Right. And then I need to know how many elements are currently in the list. Right? So I need the size of the list as well. Right? And there's my list structure. Anybody using the list, anybody using our list data type never sees this structure. Right? They never see this because all they have is the header file. Right? They don't necessarily have the source code file. They could have the compiled source code file, but they don't necessarily have the list.c file. Right? And so all they ever see is the type def for the data type. Right? So in C, this is called an opaque type. Right? It's called opaque because the user can't actually see what's inside the type. Right? So this is C's way of data hiding. Right? In Java, you would make a class and make everything private. Right? There are no access modifiers in C. So the way that you hide stuff from other programmers is you make opaque types out of them. Right? You put a declaration to the type somewhere that they can get to, but you actually define the type somewhere else, which is exactly what we've done here. Right? So the user is unable to see the data members making up a list, right? But they can still use it, right? Because they have the declaration of the type and all of its functions. All right, so when the user wants to make a list, they call one of our init functions. So I have a bunch of functions called list init something, right? And they all return a pointer to a list. Right? So they all return a list star. Right? So list init empty makes an empty list and returns a pointer to that list back to the caller. List init, where they pass in the capacity, returns a list that can hold capacity elements and returns a pointer to that list. It's an empty list still. List copy is like a copy constructor in Java, right? It makes a copy of another existing list, right? Where the other list is passed in as a pointer to that list. So that's our quote-unquote copy constructor. Init is basically would be the analog of a Java constructor. List size tells you how many elements are in a list pointed at by t. List get lets you get an element by index. Right? Again, you access the list is specified as a pointer to the list. Right? Notice that if you use an invalid index, you get undefined behavior. Right? In our case, we're going to crash the program because we're going to use assert. Set lets you set an element of the list t at that index, and it's going to set it to that element there. It returns the old element that was in the list at that position. Right? Again, if you use an invalid index, you get undefined behavior. Notice the difference between these two methods. So get, the list is a const list. Right? So get is promising not to modify the list, right? Which makes sense, right? Get shouldn't change the list. Set has to change the list, so it's not const. Right? So it actually needs to modify one of the members of the list, possibly. So it doesn't change the, it's not passed in, it's not const. Add adds an element to the list. Again, it changes the list, so the list is not const again. Insert is the function that inserts somewhere in the middle of the list. Right? So it inserts at that index, sets and inserts that element into the list. Right? It returns true if you can insert, and it returns false if it can't. Right? The only way it can't return, it can't insert into the list if it runs out of memory, which would be odd, but it could happen, I suppose. Remove removes an element at the specified index. Right? And then we've got a couple of toString functions, which I'm not sure I'm going to go over or not. They're kind of gross when you look at them. So the first one takes a list and returns a new string. So in other words, the function tries to allocate an array big enough to hold the string representation of the list. The string representation of the list is just square brackets and then the elements of the list separated by commas and spaces. The second version of list2string asks the user to provide a string for it to write into. Right? So this function requires the user to pass in a string called buff. Right? Buff has that size, so buff size. Right? And so the function will try to write into the buffer at most that many characters minus 1. Right? So it's going to try to convert the elements of the list into a string and then write that string into the buffer. Right? It writes at most buff size minus 1 characters because it needs to add the null terminator at the end. Right? So when you count the null terminator, it writes up to buffer size characters into the string. Right? It returns the number of characters that it wrote into the string. And then finally, whenever you have a data structure and you have functions like init, right? So notice init, these all return pointers to new lists. Right? The only way this can work is if it's dynamically allocating memory for those lists. Right? And so what does that mean? It means you have to free the list, right? Because you've dynamically allocated memory. Now, whoever's using the list, they don't know how that memory was dynamically allocated. Right? And so that means they don't know how to deallocate that memory either. So we have to provide a function that knows how to deallocate a list for them. Right? So almost always when you're using a C data structure of some kind, there will be some sort of function that creates a new data structure. There'll be a second function or more that will deallocate the data structure. Right? And so ours is called list free. Right? Another thing to notice is that all of our functions, they all start with the word list. Right? List something, list something, list something. Right? And that's also common in C, again, because C function names have to be unique inside a compilation unit. So anybody that uses our list data structure inside of their source code, all of our list functions have to be unique, right? They can't have a function that's the same as one of ours. So it's very common to take the name of the data structure and then stick it in front of all the function names. Right. All right, so let's look at a few of these. We don't have time to look at all of them today. So let's look at the init functions. Okay, so here's our function that allocates an empty list. Right? So to make an empty list, right, you just look at your structure and you say, well, what do I need to make an empty list given that my list is defined this way? Right? And so the size of the list is going to be 0. Right? I could make an empty, well, you could try to make an empty array. There are no empties array. There are technically no empty arrays in C. Right? So you could set the capacity to 0. Right? And you could leave the pointer to the array as being null or uninitialized. Right? So that would be one valid way to do it. But if someone's making a list, they probably want to add stuff to the list. So it makes sense to go ahead and make an array with some capacity. Right? So in other words, I'm going to dynamically allocate this array and set its capacity appropriately. So the default capacity I've got in my implementation is 4. Right? So in other words, if someone doesn't say how big a list is, I'm going to make it 4. So I'm just going to return, I'm just going to call my other init function and return a list that can hold up to 4 elements. Right? Okay, so here's list init. So this one makes a list that can hold up to capacity elements. Right? So it returns a pointer to a list. Right? So what does that mean? It means I need to make a list. Right? How do I make a list? Right? So I make a pointer to a list, and then I allocate enough memory to hold one structure in that pointer. Sorry, that's not the right way to say it. I allocate enough memory to hold one list structure. Right? So I call malloc, and I allocate the size of a list amount of memory. Right? What does that let you do? So that allocates a block of memory that can hold a pointer, a size t object, and a second size t object. Right? And so now I have a pointer to a list. Right? The array inside the list, the capacity and the size, they're all uninitialized. Right? Because malloc never initializes memory. So what do I have to do? I need to allocate the array that's inside the list. Right? So I'm going to allocate an array of int of size capacity. Right? Malloc can return null. Right? So I'm going to check. Right? Are either one of those pointers null? And if they are, I'm going to return null as well, indicating that we could not successfully allocate a list. This is this is interesting. So in every introductory C course you take, you're going to be told to do this. Right? So in other words, if you call malloc, realloc, or calloc, you should always test the pointer to see if it's not null. It turns out that on a modern computer or a modern operating system, you almost never do this. So in Linux, malloc never returns null. You can't make it return null even if you try. At some point, I'll give you a link to a research paper that tries to do this. Right? It's impossible to return null from malloc. So it never returns null. Even if you try to allocate a ridiculous amount of memory, malloc always returns a valid pointer. Or crashes your computer. Right? So it turns out that if you're programming in a desktop environment, you normally don't do this. If you're programming in an embedded environment, so something on a computer that has only a small amount of memory, then you do have to check for this sort of thing. But those are using different operating systems, right? Those probably aren't using a full version of Linux or Mac OS or Windows. Anyway, you should do this, or you should at least consider doing this. Right? Okay, so I've got my array. I've got my list. So now I can go ahead and set the array inside the list so that it points to that new array. Right? Remember, T is a pointer to a structure. So if I want to get to the member called ARR, it's T arrow. Right? So in other words, the array belonging to the list T is now equal to that array. Right? The capacity of the list T is equal to the capacity that was passed in. Oh, there should be some error checking here. This is bad. The size of the list T is 0. Hang on, just let me go back a second and see what I wrote here. Returns. There should be some error checking here. There should be some error checking. Oh wait, no, sorry, I'm being a dummy. Sorry, I programmed too much in Java for 124. Capacity is size T, so it's unsigned, so it's never negative. So you actually don't have to worry about it. Sorry, my bad. I was worried that capacity could be negative, but of course it can't. It's unsigned. All right, so never mind. Set the size to 0. Set the capacity to the passed-in capacity. This line is missing from the source code on OnQ, I'm pretty sure. And finally, return the list. Right? And so that's how you dynamically allocate a structure, and then fill in the fields of the structure, or the members of the structure, also, in this case, dynamically allocating the array belonging to the structure. Right. I guess it's basically time to go, so I'll stop there, and we'll look at some of the other functions in the next class.